Well, it's good to see so many people up bright and early, and it's going to be a nice day. So anyway, we'll start without further ado with the first speaker. It's Juan Maldacena. Not much introduction needed, but he'll tell us about something that sounds very retro, but it no doubt not.
Yeah, that was intentional. That was... Yeah, there are some people that work on something in graduate school and can never manage. Yeah, so this is some work we're doing with Ahmed Almeri and Big-Sin Lau, a student at Princeton University. And so let's first start with something that all of you know. So especially now with the advent of gravity waves, everyone is treating black holes as point particles. So if you have some long wavelength excitation interacting with a black hole, you can approximate it as a point particle. And if you go to high enough orders, you need to take into account that the black hole has internal degrees of freedom. The simplest effect is that the black hole can get deformed, and you might have some tidal deformation of the black hole, etc. And if you so that means you should think of it as a particle with perhaps some internal degrees of freedom. And of course, you know the internal degrees of freedom are at some temperature. That has to do with the size of the black hole. So the effects of the temperature cannot be treated using the long distance effective theory because they are same size as the black hole. Now for near extremal black holes, the situation is better because the temperature can be lower and the thermal effects can be treated within this low energy effective theory. Now, you all know that the near extremal black hole geometry becomes AdS2 times S2, and the entropy becomes a constant. And in recent years, it's become important that quantum corrections are not small, even though the black hole... Oh. Can you now hear me better?
Yeah,
okay, good.
Now you get feedback.
Okay.
Mentalist presence?
No?
Phenomenologist count?
Okay, so even though the black hole could be big and so that quantum gravity effects are small, there is a particular mode that becomes strongly coupled, and it needs to be quantized explicitly in the low temperature regime. And so this gives us a window into quantum gravity. So it's we're quantizing really only one mode of gravity, but well, it's some window into quantum gravity where all we need to know is gravity as an effective field theory and then quantizing this mode. So it's a solvable model, solvable corner of quantum gravity. So this mode has to do with the length of this throat. So you have this long throat, and there is some distance from the flat space region to the horizon, and that length can fluctuate. And this, the name of this mode has various names. It's sometimes called time reparametrization mode or boundary graviton. So in 2 dimensions, there are no propagating gravitons, but you can think of boundary graviton. And so you can, we can parameterize it as, in terms of a function, theta of t, where theta is the, yeah, it's here. So theta is the angle in this hyperbolic space. So here we're in Euclidean time. So this is the Euclidean AdS2 or hyperbolic space. And theta is just the standard angle, and t is the proper time along the boundary. So the fact that the boundary is wiggly means that that's related to the length of the throat that could be longer or shorter in different regions. And that makes time run faster or slower. And so if we give the function theta of proper time t, then we're also given the position of this curve relative to the center. And this is a mode, and this will be the mode that will become important. And there will be an action, and the simplest action for this mode, that the action we expect generically, and the action we get from the Einstein action, is an action that can be determined by symmetry principles. I won't explain exactly how, but it's given by the Schwarzian derivative. Okay, and it has the Schwarzian derivative has two derivatives, and so we need one quantity of dimensions of length in front, and so the theory has a dimensionful coupling, if you wish, that's related to this length scale. So this length scale tells us the length scale at which modes at which this theory becomes strongly coupled. So for short times, we have this theory is weakly coupled. We don't have to do the quantum mechanics of these modes. For times bigger than this distance Ls, the length scale set by the Schwarzian, that's what the notation intends to convey. So for times bigger than that, we have a highly quantum theory. Now this time scale is proportional to, is set by the size of the black hole, the extremal black hole times the entropy, and this is what it is for a 4D black hole. So it's proportional to 1/g Newton. So it's large in the classical limit. Now this leads to many interesting effects for the low energy dynamics of black holes that have been studied during the last few years. And this talk will be about special cases where the dynamics of this black hole is a bit different. So we'll see that we'll have a different action for this boundary graviton. So I'll discuss perhaps one case or two cases, depending on how much time I have. The main case I want to discuss is this one, the black hole interacting with a CFT2 bath. So let's start with this main case. And this was considered in the past as a toy model for an evaporating black hole in the famous paper on the page curve. And one question is, before I start analyzing some aspects of this physics, I would like to remind you some examples where this toy model is a good model for the physics of the four-dimensional black hole. Okay. Let's first start with a naive idea. So naively, you would think this might be a good model if you have black holes interacting with massless fields. So you have a 4D black hole. In 4 dimensions, we have massless photons and gravitons, so they will be interacting with this black hole, and so could that be treated as a kind of CFT? Now, in this case, there are angular momentum barriers, and if you have a low energy, let's say photon, but it has to interact through spin 1, it has spin 1, so it will have angular momentum 1, and so at low energies, the wave function vanishes at the center where the black hole is located, and there will be a suppression proportional to some powers of the frequency for the interaction between the photon and the black hole. So at very low energies, this interaction becomes very weak, and we can approximate the black hole as being isolated, to first approximation as being isolated from the exterior, and then treat the coupling as a perturbation. Okay? And the quantum effects in that language were studied a lot in these papers and several others. Now, you might think that if you have a massless scalar field, then you could restrict that argument would not apply because you would have you could have an S wave, right? So if you consider the S wave of a massless field, that's basically a 2-dimensional massless field in the radial and time direction, and that looks like it can penetrate the near horizon region. However, when you go and analyze the wave equation, you find that there is some effective potential. You can choose some coordinate, sometimes called tortoise coordinates, some coordinate where the metric looks flat. Then in that metric, the wave equation has some mass term, effective mass term or potential that's localized near the transition region between flat space. And this just comes from directly solving the wave equation. And what that means is that if you have a low energy wave, this low energy wave will not easily tunnel through to the interior, right? So, okay, so this suppresses the coupling to black hole at low energies. Now, there is another perspective for how to understand this. So we can think of the interaction, this interaction with the massless field, in terms of a scalar field at the origin interacting with the dimension 1 operator that's related to the massless field in the near. So in ADS2, you all know that a massless operator is related to dimension 1. A massless field is related to a dimension 1 operator. So we have a coupling of this form. This has dimension 1 in 4D, so there should be a factor of length, and it's the size of the black hole. Now, if you express this in terms of the massless two-dimensional field, so the field that obeys just the massless wave equation, or has a massless action with a standard, two-dimensional action in the r and t directions, that's this field chi in the external region, related to phi in this way. And so the proper coupling is between that massless two-dimensional field, which in the absence of the black hole obeys Dirichlet boundary conditions at the origin. And the coupling is to the normal derivative of that field to that operator. Okay, so this coupling, so we have the operator of dimension 1. This other thing also has dimension 1, and so has dimension 2, and that's why we have a distance scale, and that's why at low energies this is an irrelevant operator that becomes unimportant. So this is another way to understand the same thing that we explained in the previous transparency. Now this whole song and dance is just to explain why the coupling is not this. Okay, it's not. This is the naive coupling you might have written if you are told you have a massless field outside, massless two-dimensional field outside, and an operator of dimension 1, you would have written. And we try to I've given you two reasons for why that's not the coupling we should write down, one in this transparency, one in the previous transparency. Okay. I had a long discussion with ChatGPT on this. Okay. ChatGPT was convinced that this was the coupling. They always say it's very agreeable, but it did not agree with me. Okay, so the conclusion of this is that for most black holes, it's a very good approximation to go to low energies, and the black hole will be essentially decoupled from the external medium. So you have the standard isolated black hole that everyone discusses with a small coupling to the exterior. Okay? And that's good for most cases. Now, when is it not a good approximation? Well, imagine you have a black hole that has a string that ends on it. Right? So here, well, I drew 3 strings, but let's say you have some string that ends on a near extremal black hole. So then here we really have a two-dimensional field theory to start with, and we have the standard two-dimensional action on that string wall-sheet, and therefore we will have no suppression. So if we have some excitation that lives on the string wall-sheet and goes into the black hole, it just goes in through without any trouble. There is no barrier or anything like that that we discussed for the 4-dimensional case. Okay. So that's one example. The other example, which is somewhat related, is if you had a magnetically charged black hole, so there are magnetic field lines, and then you have a massless 4-dimensional charged field, then you get effectively massless 1D fields along the magnetic field lines that come from the lowest Landau level of those fields. So there are Q. In this case, in this situation, if the magnetic black hole has charge Q, there are Q massless fields that move along the radial direction. Okay. So, and an example of this would be a magnetically charged black hole with monopole magnetic charge that has some mass below a few Earth masses. So from, let's say, a gram to Earth masses. Okay, so now these were just some motivated examples, and we are also interested in understanding the solvable system to extract a little bit more information from this corner of quantum gravity. So regardless of these examples, we like to understand the solvable corner in some other circumstances. So we'll start with a simple calculation to explain what's going on in a simple context, and then we'll move on to to other calculations. So we will consider a black hole that is interacting with a CFT. So the problem we'll consider is we have a near extremal black hole in 4 dimensions interacting with this massless 2D CFT. We are going to model this by 2-dimensional JT gravity or 2-dimensional gravity theory that is interacting with has an ADS2 region, and then we'll approximate the exterior of the black hole, the flat space region, as a perfectly flat and non-gravitating background. So this background has no gravity. And then we have a conformal field theory that lives in both regions with transparent boundary conditions at the ADS boundary. Okay? So we have a CFT that lives everywhere. Is the setup clear? Yeah. So in a holographic description, we would say that we have some CFT, and we have some impurity, so some degrees of freedom here at the end, some boundary conditions, and at the boundary we could have some localized degrees of freedom, and in principle some boundary Hamiltonian. Okay, that's the setup. Hopefully this setup is clear. Yeah.
Juan,
Yeah.
is the CFT bar connected at the boundary of ADS or near the root?
This is the boundary of ADS. It intends to be here, right? This is some flat space region, and we are here. We put this at finite temperature, so that's why we have a compact Euclidean time direction. Okay. So this is basically the same as the hyperbolic disk we were drawing before, this part, and this is just a standard flat cylinder. Okay. So the goal would be very simple: just compute the free energy in this situation. Okay. Okay, so we have the usual, so in the gravitating region, we have the usual topological term and the JT gravity term and the CFT term. We have that that would couple only to the metric. So the story will be very similar to what we had to the standard story in JT gravity, where we integrate over phi, we fix the metric to be purely hyperbolic, and then we now will have to focus on the CFT degrees of freedom. Okay, so now I'm going to give you what the answer is, and then I'm going to explain how we get this answer. Okay, so what we are going to do is we are going to consider a round circle with small fluctuations, and we're going to expand only the action to quadratic order in the fluctuations. Okay, then we'll discuss what happens at higher orders. Let's, for the moment, expand purely to quadratic order. Okay, and see what happens. Now, there is a part of the free energy that comes from the bath, so from the cylinder region, the non-gravitating region. That's just the thermal free energy of this CFT. That's a simple case. And then we have some contribution that comes from these degrees of freedom that we could say are localized in impurity, or just the gravitating part of the geometry. And so from this gravitating part, well, we get some contribution from the topological term. We get some contribution from the classical Schwarzian contribution. That also comes from the JT gravity part. And then when we expand in small fluctuations of the boundary geometry of the circle, did I say how we're going to expand it? No, I think I didn't say it. So sorry, I apologize. I didn't define. So we're considering a function theta, which so we were discussing this function theta of time. We're going to be taking a function that is essentially time, or time over beta, plus some epsilon of time, right? And that's what we are doing. So then we expand this in Fourier modes, epsilon n e to the I n tau, and that's we expand to quadratic order in epsilon. That's this formula. Okay, that's the result. I'll explain in a second how we get it. Now, first, there is a familiar piece, which are, well, all these factors of n and this prefactor. That comes from the Schwarzian action. That simply comes from taking this expression, inserting it in the action we discussed previously, expand to quadratic order, you get this answer. Okay? It goes like 1 over beta. Here I've set, there is a factor of Ls here, I just set to 1. what we see is that when beta is very large, this term goes to 0, and this action becomes very small. So that means that there could be large quantum fluctuations, okay? If we only had that term. Then there is a second term that comes from the conformal field theory. I'll explain how it arises in a second. But if you wish, it's induced from the degrees of freedom of the conformal field theory. And the second term is proportional to C. And it's essentially conformal invariant. So there is no length scale here beyond so there is no explicit length scale that appears here in this term. And it's independent of the temperature. And if C is large, so if the central charge of the conformal field theory is large, this term is suppressed for all temperatures. Okay, so now let me say some words on how we compute the CFT contribution. This comes from the following thing. So we first consider a disk with some formation at the boundary, right? So we have some time reparametrization at the boundary. So that's if you wish, the shape of the gravitational manifold. And then we have this flat cylinder, and we have this function theta. So theta is a function of the proper time, and the proper time here is just the coordinate along this boundary cylinder. That's just the time at the boundary. And so the goal is to consider the CFT on a geometry where we glue point phi here to point theta phi on this side. So we glue them in this way. This will give us the CFT on some geometry, which and some, let's say, if you wish, some curved space. And the partition function of the CFT on that space will be non-trivial and will depend on theta in some way. And the goal is to understand how it depends on theta. So given any function of theta, we want to compute the CFT on this space. Now, what we know is that this space is something that has the topology of the sphere. So we can take this infinite cylinder and compactify the cylinder and think of it as a sphere at the point at infinity, right? So it really has the topology of the sphere. And you know that the metric, any metric on a sphere is the same as the metric on a, let's say, round sphere or the flat plane up to a Weyl transformation, okay? And so if we found the connection between this deformed sphere and the perfectly, let's say, round sphere, then we could use the Weyl anomaly to calculate the partition function. Okay? That's the strategy. Is everyone following? Yeah? Okay.
Can I ask a question?
Yes.
The central charge for the boundary CFT is the same as the central charge for the CFT that you get associated to the black hole inner region because of gluing?
Okay, so yes, it is not the same central charge, but it's also the same CFT. The CFT is exactly the same. The same CFT you have outside, you have in the gravitating region. I'm not using holography here. I'm just we are just discussing a gravitational background with a CFT that lives on this gravitational background.
I see.
There is no duality here. This is all purely gravity as an effective field theory. And so we have an effective field theory, which is gravity plus the CFT that lives everywhere.
Okay.
This is what you would get, for example, if you have a bunch of strings ending on a black hole, or if you had this magnetic black hole example. These are two very concrete examples.
So is it like a defect that's inside a CFT? I'm just trying to understand how.
Yeah. So the CFT lives in two dimensions. That's the radial direction and time, right?
Okay.
And it exists outside the black hole and inside the black hole. And we have this deformed geometry, and the partition function or the thermal free energy of the field theory in this deformed geometry will depend on the deformation. And that our goal now is to find the answer. So the trick to do this is just to find the holomorphic map to standard sphere. So the idea is that, so I didn't draw here, but here we have the deformed, so some function set of tau, like here. And so we can find the holomorphic map from the standard disk to, let's say, the plane, to some region of the plane, and outside from the cylinder to the outside region of a plane. And so F and G are holomorphic in their regions. And so this is, yeah. And so we now have a mathematical problem where we have these two conformal transformations, these two holomorphic functions that along the boundary circle, so along the modulus of omega equal to 1 and modulus of b equal to 1, they have to be equal, okay, in this way. So that's a well-defined mathematical problem, so we can solve this mathematical problem. In general, we don't know the general solution, but it can be solved perturbatively. So we take theta equal to phi plus epsilon of phi. So we plug it into those formulas, and we can solve it order by order in epsilon. It's just enough to solve for f and g to first order in epsilon. It's very simple. I won't show it. It just involves separating the positive and negative Fourier modes of epsilon and assigning some for it, some to f, some to g. It's very, very straightforward. And once you are done calculating f and g, then you look at the original metric that we had, and we write it in terms of the flat space metric up to some conformal, some Weil factors. Similarly, for the metric of the cylinder outside, we write it in a similar way. So in both regions, we are just writing the metric in terms of an overall scale factor times the metric of a standard flat plane. And we say, well, the partition function on the flat plane is just 1, let's say, or some known quantity. And the dependence on theta will come purely from this scale factor. And that dependence, so because we have a conformal field theory, naively, the conformal field theory should be independent of the scale factor, but there is the well-known conformal anomaly or Weil anomaly that is calculable, and we can calculate exactly what the answer is. So this is the general expression for the Weil anomaly, and we have in our case we can think in terms of a flat plane or flat cylinder, and we get this simple action. And we can also rewrite it in terms of those W coordinates and inserting the solution we found to first order for f and g, we can calculate this action to quadratic order. Okay. Is the procedure clear? After you are done doing all of this, you get this action. It is, as promised, it's a scale invariant. It doesn't depend on beta at all. It's not that we set it to 1, it just doesn't depend on beta. It also has some SL2 symmetry that's related to this action vanishing for n equal to 0, 1, and minus 1. And that's good because this SL2, we're going to treat it as a gauge symmetry of the ADS region, so that's good. And it's proportional to C because the whole effect came from this conformal anomaly, which was proportional to C. That's where the factor of C came from. And okay.
So I have a dumb question. So what do you need to add to make the dimensions work if you don't have beta?
So the dimensions just work because we have different powers of n. So the Schwarzian, let me since if you are confused about that, then probably everyone else is confused. So let me go back to the this guy here. Okay. So I'm just going to remind everyone how the dimensions work in this action. So we should think of epsilon as having dimension -1. It's kind of like a coordinate, okay? And then these n's are all derivatives, right? So yeah. So we have the epsilon -1, and then we have 4 derivatives, right? And 1 integral over time. So in total, we have 1 net derivative that is cancelled by the dimensions of beta. That's the standard Schwarzian discussion. And the difference in this case is that we don't have an extra derivative, so we don't need the factor of beta, right? So it's already scale invariant. But importantly, this action is non-local. So this term where that was quadratic in n, so the Schwarzian term was quadratic in n, so you could write it locally in position space. But this conformal, the term I'm talking about is non-local. Okay. Is now more clear? Okay. So we got this non-local action, this action. So it's scale invariant and conformal invariant, etc. But it's non-local. Okay. So I should make it big again. Just a second. Sorry. Okay. So. We go back to the expression that, I shouldn't have gone back. I had it here already. Okay, so we go back to the previous expression. And now we do the integral over epsilon. And then we get this C1 loop, which has this product, right? So the product, here I restore the factor of Ls. So we have this. This is the final answer for the one loop partition function. Okay. And so you can, by standard methods, you can calculate that determinant. And what you get is, let's say, beta to the 3/2. That's what we had when C was 0, when we didn't have the conformal filter. This came from the Schwarzian, this came from not integrating the 0 plus and minus 1 mode and scaling out this factor of beta. Well, if you didn't follow that, I can explain it more carefully. Should I explain? Well, maybe I'll explain it more carefully. So if you pull out this factor of beta from this product, you get some beta to the infinity minus 3. Okay. I forgot the 1/2 now. I realize there's. No, I didn't forget the 1/2. Yeah. So this is the same as the same product, but with modulus of n and going from plus to minus infinity, except for 0 plus and minus 1 to the 1/2. And so we pull out all those factors. You get a bunch infinite factors of beta, except for 3 factors. So and those 3 factors are these ones here. Okay. Well, I think I sketched it. I discuss it in more detail if you're curious to find exactly how you got it. Then all the poles, then there were a bunch of poles. As a function of analytic function of beta, there are a bunch of poles here. And those are reproduced by these gamma functions. And then the details of the regularization give this factor of beta log beta. And then there is a ground state energy that would depend on C and contains also divergent terms that we are going to subtract completely. We're not considering that. Okay, very good. So that's the final answer. And this answer, when beta goes to infinity, what happens is that there are some factors of gamma to the 1/2, and there are some factors of gamma to the 3/2 that come from here that cancel exactly this factor. So this, at very large beta, goes to a constant. Okay, so at long times, this really goes to a constant. Yeah.
What's the difference between?
Sorry, beta hat and beta was it's no difference. No difference. So it's whether we had the factor of L or not. It's my inconsistency. Sorry, I apologize. So this is the relation between the two, and everywhere should be beta hat. Okay. Yeah. So the new feature is that it goes to a constant. Okay. So that's the final answer for this topology at very low temperatures. Yeah.
Is there an argument that Z is supposed to be one loop exact here because the Schwarzian is and the CFT you're computing exactly, or?
Yeah, that's a good question, and no, there isn't. Okay. But I'm going to address this point here.
Oh, sorry.
Yeah. So Matt's question is related to to what happens in JT gravity. So let's just remind ourselves of what happens in JT gravity. So we have beta, the inverse temperature, and we have the classical answer essentially up to this LS, right? And if we are here, we can calculate with the one-loop correction. It becomes more important. But when we get to LS, we in principle have to calculate two-loop correction, three-loop correction, et cetera. So the theory becomes strongly coupled here. And in this regime, you really have to solve the theory non-perturbatively. So it's not enough to go to high orders. And fortunately, this theory can be solved non-perturbatively. We find the exact answer. So Stanford and Witten, for example, derived very nicely the exact answer. Other people had also derived it before. So we have now methods to do that here. Now, how is the answer different in our case? So here we have the JT classical answer. And when we get to a length scale, which is LS over C, so before the Schwarzschild becomes strongly coupled, we have the transition to the regime in which CFT corrections become important, right? And that's what we just computed. But if now, the point is that the coupling was becoming, the effective coupling of these theories was becoming stronger, was very, very weak here, and it was becoming stronger. But when we get to this point, it just becomes constant, okay? And then you continue with constant coupling, which could be weak. If C is large, the coupling will be weak. So there is a new expansion parameter, which is 1 over C, right? And the leading order is conformal invariant, and we expect that all the 1 over C corrections will continue to be scale invariant and independent. So indeed, there will be corrections, but we expect that they are suppressed by 1 over C and not enhanced by factors of beta. So this result that it goes to a constant, we believe is exact in the 1 over C expansion. Though maybe the precise value not, but that feature should be true. Okay. So well, that's what I just said, that the full range remains classical for large C. So that's a new feature. Now, I should, what is that length scale? So there was a length scale that we mentioned. Yeah, so what is this length scale? So this length scale has a physical meaning in this context. And it's the length scale that sets the evaporation time scale of the black hole. So if you have this black hole interacting with massless fields, and you throw matter in, the black hole will evaporate by emitting this massless, the CFT degrees of freedom. And the time scale over which it will evaporate is set by that time scale tau. That means that we'll have the energy of the black hole will decay exponentially with a time scale set by tau. Okay, is that clear? Okay. Good. So we can also roughly call it the mass of the boundary graviton. I mean, if we take that action that we discussed previously and set it to 0, you find an energy, a complex, energy which is given by this. Well, the inverse mass would be this tau. It's not really a mass in the sense that we don't have a quadratic action where we have this mass squared. It's more like a quasi-normal mode, a decay time of the black hole. Okay, so now also we can call this low energy regime as induced gravity in the sense that the action, so there is a gravitational degree of freedom, which is this time reparametrization, but the action is not coming from the Einstein action, it's coming from an action that is induced purely by the matter that propagates on this geometry. Now, just for fun, we can put in some numbers for these magnetic black holes of the standard model. So we have one of these black holes, let's say, and here we plot the mass in kilograms. I went to the low mass range, like 1 kilogram, let's say 1 ton, 1,000 kilograms. Now, in this case, this time scale, this transition time scale, is this curve here, and here is the temperature in electron volts. Okay, so this is 1 electron volt, right? That's roughly visible light. So you have so you see that you are well. So for let's say this range of masses, For, let's say, laboratory scales, you are well in this regime. Okay. This is what you see if you. This is the regime you see if you look at these black holes with your eyes. Okay. Now, maybe I should have mentioned. I had this other curve here. So this is the curve that will give you the just set by the Schwarzian. So this is the curve you would naively calculate by ignoring this effect, and this is the correct curve where you include this effect. Okay. So now we want to consider some kind of scattering experiment. So just throwing something into the black hole and watching it evaporate and seeing what happens in this regime. So what we're going to do is we're going to basically do the same calculation we discussed previously, but inserting some operators. So we're going to insert two operators that will have left and right moving parts at 2 points, and we're going to basically do the same thing we did previously. We'll calculate this 2-point function, but after integrating over these boundary gravitons and see what we get. So we do exactly the same as before. So given a reparametrization, we solve this problem, which was to find the functions f and g that we discussed previously. We compute the Liouville action. We compute how there is also a contribution of the functions f and the function f to this 2-point function. We integrate, we expand perturbatively. We integrate to second order in epsilon. And first of all, let's try to before I tell you what the answer is, let's just see what we expect to find. So in the regime we're considering a very long time regime. So the black hole evaporates almost instantaneously. So you send some excitation to the black hole evaporates almost immediately. So what this means is that in this regime, there is no energy that goes into this gravitating region. So somehow, as soon as energy wants to go in, it gets reflected out. Okay. So the stress tensor essentially at this boundary obeys that t++ is equal to t minus minus, or that there is no flux of the energy into the gravitating region. And so that's what we expect. Now, here on the left side, we have basically the CFT vacuum. So from the point of view of the CFT, we can think of this as an infinite cylinder, if we wish, with the CFT vacuum. And so this type of conditions, so saying that we have here the stress tensor equal for left and right movers, and that we have the vacuum on the left side, is what in boundary conformal field theory is called the Anishi-Bashi state in the closed string channel. Let me just review what that is for those who don't know. So this is sometimes denoted as 0 with double bracket, so that means the Ishi-Bashi state. So let me just review quickly what that means. So this is a state that is defined by this condition. So you have the Virasoro generators, left and right moving Virasoro generators, and we impose that. So we're thinking of this in the closed string channel, quantizing sort of in the radial direction, and then this boils down to a bunch of equations which you can solve, and you find that this state is basically a sum over all the conformal descendants of the vacuum here on the left movers, and exactly the same, let's say, an orthonormal basis here, and the same orthonormal, the same state for the right movers. Right? In other words, if we were to flip this brat to a cat, this guy would be essentially like a projector onto the zero, onto the identity state. So that's what you get. Now you can also solve this for large C, and in that case you find that it is the vacuum plus then some terms that start some expansion that goes like 1 over C, and some further corrections. So you can also do that. So this gives the leading correction, and this will give a correction to the 2-point function that we were discussing, and that. So this is just computed using this Ishi-Bashi state idea, but what you get using this method agrees with what you get by using gravity when we expand to quadratic order in epsilon. So I didn't show it to you the gravity computation. Is very similar to the one we saw previously for the partition function, but it gives an answer which agrees with what we would have obtained from the Ishibashi state. And more precisely, if you calculate the corrected two-point function divided by the uncorrected two-point function, it's basically 1 plus some small correction, and the small correction is some function of the cross ratio. So this is consistent with the idea that what we get in this regime is conformal invariant, so things depend only on conformal cross ratios. Anyway, so that's what we get, and this agrees with the formula. Yeah. So okay. So this is what you get just directly from gravity, and agrees with the 1/c term in the Ishibashi state expansion. Okay. Very good. So what things can we learn from this calculation? Well, basically we can do the same things we normally ask when we calculate 4-point function. So morally here we are calculating a 4-point function because we have left and right movers, right? So we have basically 4 operators. And this calculation shows also maximal chaos. So if you do the out-of-time order correlator the usual way we calculate them, it continues to display this maximal chaos. This was perhaps not 100% obvious because maximal chaos we expect it whenever we have gravity. Here we have some action that got induced from the CFT, so it wasn't 100% obvious, but not completely unexpected. And the mathematics leading to this is very similar to the mathematics that leads to maximal chaos in the discussion of ADS3, of the ADS3 computation where we have the identity conformal block changed. Okay, so far we discussed the leading order answer in a 1/c expansion, but we expect that the exact answer from the arguments we discussed, that the exact answer should be given by taking the 2 left-moving operators, fusing them to the identity, and then similarly with the right-moving operators, and then considering here the identity conformal block. Okay, so that's supposed to be the exact answer. Okay. Now, can we justify this exact answer a little more? So we can. One thing we can say is that the Schwinger-Dyson equation for this functional integral that we're doing in this regime where we neglect the Schwarzian, we can calculate the Schwinger-Dyson equation, and the Schwinger-Dyson equation imposes this condition at the boundary. So that's what the equation is. So we expect that therefore we should get this Ishibashi state discussion. And so this would suggest that this is the result at any C. So we can now extrapolate and see what we get if we go to small values of C. So for example, we can get, let's say, C equal to 1/2. So what exactly do we get if we go to C equal to 1/2? But before we go to C equal to 1/2, let me just say a little bit more about the physics of this. So what this is saying is that we send some stuff into the black hole, right? And the black hole evaporates, but it evaporates basically through the emission, through the evaporation process. If you think of how the Hawking radiation arises in this discussion, it arises by doing conformal transformation and so on. So it's mediated by the stress tensor. So the outgoing particles are purely excitations produced by the stress tensor. And that's basically what we see in this discussion, that we have here stress tensor and its descendants that are being exchanged and are producing, let's say, the left movers from the right movers, if you want to interpret it that way. Okay, is that clear why we are supposed to get this? Yeah. Okay. Now let's extrapolate to C equal to 1/2. So here what we're imagining is that we have a black hole. The black hole could be big and so on, but the only degrees of freedom that are interacting with the outside is just the Majorana fermion. So we have this Majorana fermion. And in this case, if we consider a situation where we have an even number of Majorana fermions left and right movers and the identity, then we get, so in that case, when we fuse all the fermions and we project to the identity, it's the same as if we had done no projection, because when we have all this even number of fermions, the only operator that could propagate in the Ising model in this situation is just the descendants of the identity. So this is the same as doing no projection. And what this essentially means is that these fermions are behaving as if they were reflecting from a mirror. Okay? So in some sense, for this case, the black hole is a mirror. Now, if we had an odd number of fermions, then we would have here the operator with the Ising notation is called epsilon, which is basically psi itself, so descendants of psi. And this guy is projected out by this condition of having the 0. So we would get 0 for this guy. So how do we interpret? So we'll interpret this later. We'll explain it a little more clearly. So far, this is just an observation. In this Ising case, we actually do not get the OTOC, so we don't get chaos, because that's what we got from the first term in the 1/c expansion of the conformal block, that we got the OTOCs. If we look at the same thing with the conformal blocks of Ising, we do not get that. So and that makes sense. And notice that we are deriving this just from a gravity computation, right? So we're saying that when a black hole evaporates in the presence of this Ising model, we don't get a chaos result. So now let's go back to the large C case. And this is just trying to explain a little more what's going on. So here, we imagine we send in from the exterior some excitation into the ADS2 region. Let's imagine this in, let's say, Poincare coordinates. So we are finding that in the energy contained in this excitation, here I try to denote this in blue. So this energy gets reflected immediately. And some other information that was carried by this particle continues to the black hole region. Okay? So from the point of view of the excitation in the CFT, that excitation just travels through, goes into the interior, doesn't realize anything is going on. But somehow the energy has been taken out and sent here to the exterior. So that's what we get in this regime. Okay. Now, these Ishibashi states are familiar from the study of conformal boundary conditions. And a good conformal boundary condition is given by a combination of those Ishibashi states, which is called Cardy state. Okay? And those are the ones that correspond to real local reflecting boundary conditions. And this linear combination involves finitely many terms in cases of rational conformal field theories. So for example, in the special case of the Ising model, there are 3 possible Cardy states that correspond to the spins fixed plus, minus, or free. And they're this combination of the so-called Ishibashi states. Now, in particular, for these 2 states, we have that the reflection condition for the fermion, so the Majorana fermion, is that when it hits the boundary, it gets reflected with no sign change. In this case, it gets reflected with a minus sign change. Right? So very simple reflection matrices in these 2 cases. Now, when we construct 0, we have a linear combination of these 2. And basically, when now we send the fermion to this 0 Ishibashi state, what is happening is that there is some interference between the terms that give us a plus sign and terms that give a minus sign. And so when we get an odd number of fermions, it vanishes. When we send an even number of fermions, all these minus signs cancel, and we get the same as what we sent in. Now, recall that we have a black hole with a big S0. So what that means is that, for example, in this case of Ising, it's not that we have just one of these Cardy states, but we have, or this particular superposition, we have this whole thing multiplied by e to the S0. So we have e to the S0 of each of these guys, right, in roughly this proportion with the square roots and so on. Okay? So you could imagine that the, well, maybe one. Okay, so in this example, we see that we have a superposition of Cardi states, and it leads to some interference and information loss, right? And it looks like this apparent information loss, it has to do with the fact that we have this superposition of many different Cardi states, each of which has a unitary reflection matrix, but they are all being interfered. Okay. So this is the same. So what I was trying to mention here is that, well, the black hole behaves a bit like a mirror for energy. So in some sense, if we look at how energy gets reflected from these black holes, we'll see a shiny little black hole. Okay, so can we get other Ishibashi states? That's one question we can ask. Oh, I'm almost out of time. Okay, yeah. So so you can get other Ishibashi states by deforming. So instead of having a conformal field theory here in the gravitating region, you can make it a non-conformal theory by adding some operator that you integrate. And to first order in the deformation, you would get a different Ishibashi state. And anyway, then you could also ask about higher order, higher genus corrections. That, in principle, well, it's ill-defined. So we'll make some observations now. So the first thing is that it's ill-defined because there are regions where the geometry in between can have narrow necks. But you could, that will lead to divergences. But the idea is that perhaps we can extract these divergences by renormalizing the zeroth order term. So for example, when we have the ground state propagating here, then this looks similar to what we would get just purely from a disk, just a pure disk here with the vacuum. And this could be viewed as a renormalization of e to the s naught. And interestingly, in this situation, you can repeat many of the things you normally do for JT gravity. They are also present in this regime. So if you ignore this, so you ignore this issue, or you think you renormalize it this way, then you can consider some other variants. For example, connecting the two CFTs would lead to a traversable wormhole solution for large C. And this traversable wormhole solution is such that, well, this length outside of the CFT is something that you completely fix. And then the theory finds its own length of the wormhole inside. And it turns out that they are exactly the same. So what that means is the following, so that the conformal diagram of this type of wormhole looks as follows. There is a piece of a cylinder. Here I've took this wormhole and consider the Lorentzian version. So here we have a segment that has length L external, and then there is another segment that comes from the gravitational region. If you send the signal from the exterior, it goes through the wormhole and it emerges on the other side, right? After some time. So this time is the time it takes to go through the wormhole, which is equal to this. And then, for example, the energy of this excitation gets reflected, and it reaches the other side. So there is the time that it takes to go through the exterior of the wormhole. And in this case, they're exactly equal. Now, just by causality, we expect that this time should be shorter than the other. But in this particular setup, they are exactly equal. So it's barely consistent with causality. Okay? And the usual entanglement interpretation and teleportation interpretation of this type of solutions. Okay. So this is similar to what was before, but with some slightly exotic properties. And so here there is some entanglement between the two sides, and I guess the entanglement are the possible Cardi states and the possible boundary conditions. Okay. Now let me finish. Well, this is I'm out of time. So now what we expect under general principles is that in a situation like this, we are supposed to have some impurity degree of freedom here. But if we go to very low energies, this should flow to Cardy boundary condition. In our case, we have very large S0, very large entropy, so we would expect that it flows to a collection of Cardy states, right? That's one thing we might expect, or that it flows to just a single one. That would be the most obvious expectation for the case of for example, when we have icing outside. So for example, in this simple case of icing, we start with this, all multiplied by e to the S0. It means we have some kind of Chan pattern factors for each of them. And then, so for each of, so it's similar to the, so it has indices, so each of these things have some indices. Each of the boundary conditions has some index, right? Each plus has a bunch of indices, minus a bunch of indices, and so on. And so it's similar to the indices of D-branes. And there could also be off-diagonal deformations that would be RC flows that, let's say, connect plus and minus, for example. And those would combine Cardy conditions into a smaller number and would reduce the total number. It could reduce the value of S0. Now, we don't see that happening at the level of the disk, but it could happen once we include some higher genus corrections, or I'm not sure whether it's forced to happen or not. This is what we would expect to happen just under general principles. But we haven't seen this happening from gravity. OK. So anyway, maybe I'll skip this. So conclusions is that we have discussed some aspects of JT gravity plus a CFT in the low energy regime. The bath dynamics does not decouple to low energies. The black hole is a mirror-like energies. And the black hole, you can view it as a superposition of D-branes or Cardy states, right? So that's what's the D-branes in the title. So we see something like, D-branes emerging directly from the gravity region. Now, you can ask a few questions like how much remaining dynamics you need to add to what we discussed to reproduce gravity, so it's higher genus corrections. And, well, how much of this dynamics is embedded in the reflection matrix of each Cardy state? What can we say about the statistics of these reflection matrices from the gravity computation? And how much of the gravity is encoded in some aspects of the matrix structure of what the operators are in terms of the matrix indices of these D-branes. OK, thank you. I'll finish here.
Question, Ying?
I think maybe I misunderstood something. Can you elaborate more on what you mentioned, that information loss?
Yes. So when that was at the disk approximation that we discussed. So if you send in some let's say you have a CFT that has let's say two icing particles, right? So you can send one or the other, and so you'll see that you send particle number 1, you will have Hawking radiation coming out that will not have the information about the fact that it was particle 1 or particle 2. Let's say you have 2 fermions. So I discussed the case of 1 fermion. Now we discuss 2 fermions. So you can send fermion 1 or fermion 2. What comes out is just some Hawking radiation that doesn't know about fermion 1 or fermion 2. This is what usually happens for black holes.
Yes, but I thought with a full consideration that
Yes.
from the work, let's say in 2019, it's the information eventually people concluded is not lost. So it's
yes. Well, we haven't considered. Well, okay. You would reach the same conclusions if you considered replica wormholes and so on, which we have not discussed.
This is effective field theory.
Here I'm doing the simplest first pass on this, which is to analyze just the disk. So the disk displays information loss. Is completely standard.
Oh, I see.
Yeah.
Thank you.
And then as you consider the higher genus, you should recover the effects that tell you that you have information preservation. Yeah. No, there's nothing inconsistent with. I'm not claiming that we're predicting information loss. It's just trying to understand how that is related to let's say the fact that we have a superposition of Cardy states, for example.
Oh, thank you.
It's a particular setup. I mean, it's of course the general topological discussion will be the same as the standard discussion, because that discussion doesn't depend on the details of the dynamics of gravity, only depends on topological aspects. The only aspects of these talks is just to understand the dynamics. So changing it from Schwarzian dynamics to this dynamics of, let's call it gravity, well, CFT-induced gravity. That's all it was.
Matt?
Just maybe a question about this last point. So you sort of gave the two examples of CFTs being the magnetic black hole example and also some 2D like string world sheet that ends on the black hole. So in the example then of the string world sheet example, is it literally the D-brane boundary condition that appears? Just elaborating on the point on the slides. Is it?
Yes.
Yeah,
we expect something like this. It's a zero-Ishibashi state.
Right.
We haven't recovered yet the correct D-brane boundary condition.
Okay. Right. It's not.
So, for example, if you have the heterotic string and you had all the internal directions, you don't get the information about what.
Right. Okay.
Yeah. So, I think to recover that you'll need more work.
Mm-hmm.
But it also is not the world sheet D-brane boundary condition. It would be like a space-time.
Okay, yeah.
So it's slightly different. Maybe my title was slightly misleading, but I wanted to draw an analogy only. It was a bit of a nerdy joke. That's all.
Shota.
So this gravity computation, can you extend it to the case where left-moving center charge and right-moving center charge are different? Because in that case, defining the Ishibashi state has a problem.
I haven't thought about this. I would expect no, because the theory would have a gravitational anomaly, and you wouldn't be able to couple it to gravity in the gravitational region. But I don't know. Maybe you can. I don't know if you can do something that makes it work.
Neil?
So you said that in this ADS2 region, when you couple it to the CFT, the black hole discharges exponentially rapidly? Did I hear that correctly?
Yeah. So, the black hole evaporates with a time scale which is 1 over that time scale Ts that we were discussing, right? So that's how quickly the black hole loses its energy.
Where Ts is?
Ts was Ls over C. And Ls was the Schwarzschild rate. So this is in 4 dimensions. It was equal to this.
So just trying to understand physically what's going on. So
so we're considering the system. What's going on is very simple. So we're considering the systems at timescales much bigger than this. So at timescales much bigger than this, the evaporation is instantaneous. So you send something and immediately you get out. At this, when we look at the system at a very long timescale.
So, is there some computation I can do? It sounds like there's some radiation rate, which is being governed by the fact that the ADS2 black hole is emitting Hawking radiation at some steady rate, and then the more scalar fields I add, the faster it's evaporating.
Yes, let me derive this time scale. This was done in the paper that I cited by Mertens, Berlinde, and Soy. So the idea is that the energy in the Schwarzian theory is proportional to this Schwarzian length times the Schwarzian, right? Okay, that's what the energy is, the expression of the energy. I discussed the Lagrangian. Now the Hawking radiation rate, right? The energy loss is proportional to. It's related. So when we have some time reparametrization, we have some new vacuum and so on, and we have to do some transformation, and that transformation is related to that same coordinate transformation we're talking about, and so the radiation rate is proportional to the stress tensor of the CFT, right? And that stress tensor of the CFT is proportional to C times the Schwarzian itself, right? Okay. That's the anomaly piece in the, and that gives the radiation rate. And so now you put in this equation, and this is saying that Ls times the Schwarzian dot is equal to C times this, right? That means that this Schwarzian is going to behave like e to the minus t over tau, right? Where tau is given by that quantity. I mean, this ratio Ls over C is what,
Okay.
well, it appears because of this
So
equation.
from the point of view of the ADS2 region, it is just standard Hawking radiation.
Yes. Nothing that I discussed is something fancy. Everything that I discussed is standard Hawking radiation. The only perhaps exotic thing is that the dynamics of gravity is induced from the CFT. That's the only exotic thing.
But then wouldn't you expect when you're sending in some pulse
Yes.
that it doesn't reflect immediately, that there's some time scale over which...
Yes, the time scale is tau s,
Yeah.
this time scale. But
So
by
it's-
definition, let's say, we are only considering the system at times, right, which are much bigger than this tau s, right?
Okay.
Yeah, so for example, for this case of the magnetic black holes, you have a magnetic black hole of 1 kilogram that you can have in your lab. You look at it with light, right? We are in this regime. We are in this regime. So it's not like it's an impossible regime.
Okay.
All right, we have a delicate competition between more questions and coffee. So any more questions? One more.
Yeah, so I think I remember that if you just have the Schwarzschild theory and deform by an irrelevant operator of dimension between 1 and 3/2,
Yes.
then this is also a case where...
Yeah, that's another case. That was the second case I was going to mention, but
okay.
I will not use it as a bait to go. But yeah, that's another situation where the action is not given by the Schwarzian.
But that's really a distinct scenario from what you're discussing.
Yeah, it's different from this. I mean, different in detail, more or less, somewhat similar. So it's different. So, okay. The difference in that case is that the action is, again, non-local and different, but it does not entail communication with an external path. So it only has something to do with what's going on at the boundary. That's one difference.
Yeah.
Conceptual difference.
All right, let's thank Juan